The results that we present in the article were obtained within the framework of the project Quantum Dynamics of Beams with Phases and its applications. The goal of the project is to comprehensively study the properties of vortex quantum states of photons, electrons, and other particles, their dynamics, methods of generation, interaction with other systems. In particular, in this article, we study how the orbital angular momentum of a vortex electron can affect the characteristics of the Smith-Purcell radiation. A vortex electron is a special quantum state of a free electron in which the wave function is characterized by an orbital angular momentum. The Laguerre-Gauss wave packet is an example of such a state. In particular case of zero principal quantum number, the probability density of such a state is concentrated in a donut-like shape. The propagation of such a wave packet resembles the propagation of an air vortex or smoke ring. The Smith-Purcell radiation is a relatively simple way to generate quasi-monochromatic radiation from charged bunches passing near a conducting diffraction grating. It has been proved to be useful in developing compact free electron lasers and high-resolution sensors for the particle beam diagnostics. The Laguerre-Gauss wave packet has internal multiple moments, such as magnetic dipole moment and electric quadrupole moment. As a result, the interaction of such a wave packet with lattice, with conducting grating, is slightly different from a Gaussian symmetric wave packet. This difference will manifest itself in the radiation. To put it differently, we can see the shape of the wave packet and its spreading by observing Smith-Purcell radiation. A free wave packet, regardless of its shape, undergoes spreading. For a vortex electron, this leads to an increase of its quadrupole moment. The radiation of such an increase in quadrupole moment is coherently summed along the grating and results in the nonlinear amplification.
I would also like to say a few words why it is so important to study electromagnetic radiation from vortex electrons and in particular Smith-Purcell radiation. The thing is that normally we have non-linear effects in radiation when we have beams of many electrons. But here we deal with a single electron packet, and already at this stage we have non-linear effects, non-linear enhancement of the radiation losses when the radiation power depends on the number of strips of the grating non-linearly. So this is because there is some kind of internal dynamics inside the electron packet that generates this Smith-Purcell radiation interaction with the diffraction grating. So there is internal dynamics is related to the packet spreading, and when the grating is longer than the packet's relay length, then there is an enhancement, and such an electron would lose its energy much faster than an ordinary electron does.
The quadrupole moment has a cubic growth with the length of the grating. This effect also depends on the polar angle, and one can see small shift of the maximum of radiation intensity with respect to the polar angle. For instance, a 4-degree shift of the polar angle of the maximum of Smith-Purcell radiation presented in this figure can be achieved just with orbital angular momentum equals 10, and the initial wave packet radius is about 20 nanometers. Vortex electrons with such parameters can be generated using available experimental setup. Thus, we believe that our results, our work can be interesting both to the theoretical and experimental physics community.